All right, so thank you to everyone who organized the Octoberfest. I'm really excited to be here talking to you about some of my recent work in category theory, namely this perhaps novel branch of category theory, which I have dubbed paranatural category theory. So I'm really eager to get some of your thoughts on this and hear what you have to say about the ideas that I'm putting forward in this talk, and particularly if you've seen this is a topic that has really dense connections to a lot of other fields. So I'm eager to hear if you've seen these concepts or these ideas in a different guise elsewhere. So the paranatural category theory is really concerned with what I'll call difunctors, which are functors of this shape, of the form ℂop times C to set. So I think profunctor is maybe a more common term for this concept, but I think it's a little more general. Often ℂop times D to some other category or variations on that. So I'm just going to be fixing the term difunctor to mean a functor in two arguments, one contravariant and one covariant, that takes values in sets. And the notion that, or the kind of question I want to ask is what are the appropriate notions of transformation between difunctors? And so this might not seem like a very interesting question, or this might be seem like the kind of question that was solved a long time ago with the very advent of category theory. Namely the notion of a natural transformation. So these are so difunctors are just a particular kind of functor, and so of course we can with given two difunctors from the same category, we can. Oh, sorry. Well, could someone? Okay, thought I heard something. So a difunctor is these are just an instance of functors, and so we can have a natural transformation between them. And this is, of course, a well-known notion and a very well-studied notion. And for many applications, it's just the right concept. But one thing I want to note about natural transformations in this case is that a natural transformation is going to be doubly indexed over the objects of the category. So for objects I and j of the category, for every pair of objects I and j, we're going to have a map alpha ij, if alpha is a natural transformation, from gamma ij to delta ij, if it's between gamma and delta. And so in some cases, this is what we want. In some cases, we don't want to index twice over the objects of the category. We actually only want to index once. And so natural transformations are not the right concept when we're interested in kind of diagonal transformations. And so an example of this would be if we try to do a category theoretic treatment of the Church numerals. So a kind of canonical example of a difunctor for any category C would be the ℂ functor, which is, of course, contravariant in one argument and covariant in the other. And so this is a difunctor. And so if we look at endo transformations on this ℂ difunctor, one such thing that we can kind of put together is the so-called church numerals. So for any natural number n, we can encode that natural number n as a family of maps, taking this diagonal ℂ set from J to itself to itself. And so it takes so the church encoding, or the church numeral corresponding to n, would be this function that takes an f and returns the n-fold composition of f with itself. And so this is a notion we can define. And so this would be a family of maps indexed over the objects of J. But note that it can only be indexed once over the objects of J. So the domain and the codomain, in order to be able to self-compose, the domain and the codomain have to match. And so this is a family of maps, and it's a kind of transformation from ℂ to ℂ. So it sort of looks like a natural transformation, but it isn't a natural transformation because like I said, a natural transformation from ℂ as a functor to itself would have to be doubly indexed over the objects of the category, and this is only singly indexed over the objects. And so, of course, there is a known solution to this, namely the notion of a dinatural transformation or a diagonal natural transformation. I believe these are due to de Street, and then a definition of dinatural transformation appears in MacLean, so it's a pretty canonical notion in category theory. And so a dinatural transformation, what it is, it's also a family of maps, but it's only indexed once over the object. So the category, and it goes like these church numerals, it goes from the diagonal application to the diagonal application. And then there's and then subject to so all of these notions are going to have a family of maps subject to some condition, and the condition for dinaturality is that this for every morphism I2, this hexagon that you can draw together using the difunctors gamma and delta and the family of maps alpha, this kind of the first diagram you'd come up with is this hexagon, and so the dinaturality condition is that this hexagon commutes for every I2. And so this is a fine notion, and there are a number of things that you can do with dinatural transformations, but they're also a little bit inadequate as a notion for a couple of reasons. The one that's kind of most commonly cited in literature, and again, this is mentioned in MacLean, is that there's no way to compose dinatural transformations. So if I have a dinatural transformation alpha from gamma to delta, that will tell me that this diagram is for any I2, any morphism I2 from I0 to I1. The fact that alpha is a dinatural transformation from gamma to delta would tell me that this hexagon commutes. And then if I have a beta, which is a dinatural transformation from delta to theta, then that will tell me that this hexagon commutes. But in order for their composite to be able to count as a dinatural transformation, I would need to be able to conclude that this outer hexagon commutes, and I don't have the information I need. That doesn't follow, and there are known counterexamples where these don't compose, and so this is a pretty serious shortcoming if we're interested in this as a notion of transformation. Because of course natural transformations can compose, and generally we want to be able to compose two transformations in general between difunctors. So this is a pretty serious shortcoming. There are some classes of dinatural transformations that have been identified that compose. So in particular, the church numerals I mentioned are dinatural transformations, and they do happen to compose. The composition of church numerals is multiplication. But I think the most interesting class of dinatural transformations that compose, and the one that this talk is kind of centered around, are so-called strong dinatural transformations. So a strong dinatural transformation, I'll give the definition in a second, but a strong dinatural transformation is also it's a particular kind of dinatural transformation. So it's the same data. It's indexed once over the objects of the category, and is defined as these family of maps on the diagonals. But we have a stronger dinaturality condition for this notion. Which I think, and I'll go over that in just a second, but I think makes it a better notion. And so, in a way, I view this notion, the strong dinatural transformation, as really as the fundamental, or at least a fundamental concept in its own right. And so, for this reason, and as well as several others, I advocate rechristening these as paranatural transformations, and the para is a reference to a theory in theoretical computer science known as parametricity, which paranatural transformations have a really deep connection to. And so so let me go ahead and define so henceforth I'll be using the term paranatural transformation to mean strong dinatural. So if you look in the literature, you'll find strong dinatural, or Barr dinatural is the term frequently used, but I like paranatural. And so here's the definition of a strong dinatural transformation, or a paranatural transformation. So it's a family of maps indexed on over the objects of the category, the domain category of gamma and delta, and it's defined on this diagonal. I'll use this notation to mean that alpha is a paranatural transformation. This arrow with a diamond over it, and you'll see where the diamond bit comes up. But so here's the definition: is that the naturality condition, or the paranaturality condition that we need, is that instead of this hexagon commuting where this span over here was gamma I1 I0 and two applications of the functor. Instead, what I do is I form this cospan here of the here I'm applying the negative morphism, or I'm applying the morphism I2, the negative portion contravariantly, and then here I'm applying it positively to get from these diagonal sets into, and this, by the way, all these diagrams are happening in set. So I can make use of the fact that it's set, since that's the codomain of my functors. So I take this cospan here and I form the pullback of it. And then the requirement for a paranatural transformation is that the resulting hexagon, outer hexagon, commutes. So that if I, this vertex here is the pullback. And there's a number of equivalent ways of stating this that exist in the literature. I think it's informative to spell out what this means, or one equivalent way is just to spell out what it means, since we know how to take pullbacks in set. And what that says is that if I have any element of the set gamma I naught, and any element of this set gamma I1 that get mapped by these two maps to the same element of gamma I naught I1, then I can apply alpha I naught to those two, and alpha I1 to those two elements, and then they will get mapped to the same thing by the corresponding morphism components of delta. And so we can phrase this as diagrammatically as if this diamond commutes, then the outer hexagon commutes. And so it's relatively easy to see that relatively straightforward to see that this is any paranatural transformation is going to be a dinatural transformation. So it is a strengthening of the notion of dinatural transformation. So that's the definition. And then there's a number of really interesting results that come out of this. So first of all is that the Church numerals are indeed paranatural transformations. So by restricting this notion from dinatural to paranatural, I haven't lost the Church numerals, which is kind of you may or may not care about doing Church encodings in category theory, but I think it's an informative example, and a pretty canonical example. So it's good that we still maintain it. And this is the real improvement over dinatural transformations is that we get the pointwise defined composite. So if I just kind of stick the diagrams together, then I do get the composite is a paranatural transformation. And so intuitively you can think about this as the reason that natural transformations compose is because if I take two rectangles and stick them together, I get a bigger rectangle. So naturality squares, or naturality rectangles, I guess, compose. But dinaturality didn't work because if I take two hexagons and stick them together, I don't get a bigger hexagon. You can't like join two adjacent hexagons to get a bigger hexagon. But here in this diagram, I have these kind of I call them commuting chevrons. This kind of like angled shape here. And if you stick two of those together, you do get. So if I had a further beta that goes on further here, and then then I could just get a bigger commutative chevron. And so that's the kind of simple way to see why this works out is that yeah, you can't compose two hexagons together to get a bigger hexagon, but you can compose two chevrons together to get a bigger chevron.
Jacob, can I interrupt for a minute?
Yeah, of course.
A question in the chat.
Oh, absolutely. Let me see if I can.
Oh, it's just actually it's just to me, so I'm going to ask Fosco to ask his question directly.
Okay.
Yeah, thank you. So I find this definition interesting and a bit funny because it's clearly asymmetric. You're asking a condition only on one side of the hexagon through a pullback square. Why don't you ask instead a condition with a push-out square, and why not both? Because this looks very strange. For example, this notion will lead to a different definition of a co-wedge, where the codomain is constant.
Okay. That's an interesting question. So, I mean, this you can make this somewhat more. There we go. Yeah, you can make this somewhat more symmetric. In that, you know, I'm doing a pullback here on gamma, but I'm not really doing a pullback here on delta. If you kind of think through it, these maps, I mean, you know, I'm also requiring here that these you know, I'm the same kind of condition of like I have a thing here and a thing here that map to the same thing here. And so yeah, you can view these as kind of equivalent to maps of pullbacks. So you do get a little bit of a pullback on both sides if that's that's one of the kind of equivalent ways of stating this. As for whether we should use pushouts, there is a sense in which we can dualize these. I'm not going to have time to talk about it. To talk about these and talk about it in detail on the in this talk. But at the end, I'll link to an archive preprint where I cover the kind of corresponding end and co-end calculus here. And there you do get a kind of a nice you do get a kind of duality. And so I haven't thought about whether that arises as some kind of a push out corresponding to this pullback, but yeah. So yeah, your taste may vary in terms of whether you like this definition or not, but that's that. This is the definition at least. Thanks for the question. All right. So yeah, so we get these compose. In particular, they compose associatively, and the paranatural transformations include. You can view the identities as a paranatural transformation. And so we can define this this category whose objects are these difunctors. So there's one of these categories of difunctors for each category C, whose objects are difunctors and whose morphisms are paranatural transformations. So maybe this isn't the best notation. It's a little bit annoying to have to write, but I thought it was kind of a cutesy notation to write this as C diamond, kind of by analogy to the standard notation for the category of presheaves as C hat. So this is kind of we're doing the covariant and contravariant version of that. So it's a little bit of a play on that, and also the diamond notation that I've been kind of establishing for this. So we can define this category. So this is again something we couldn't do with difunctors, or sorry, with dinatural transformations because they didn't compose. But now since we have composition, we can talk about this category that's kind of again analogous to the category of presheaves and natural transformations. And this analogy carries through surprisingly well. So first of all, we can show that this category of difunctors has all finite products. So the terminal object is of course just the difunctor that returns that constantly returns the singleton set, and the binary products are defined pointwise. So nothing too surprising there. But maybe a little bit more interesting is that we can view this category as this category is Cartesian closed. So we can form exponential objects for it. So if you remember when dealing with the category presheaves, how we a kind of standard argument for how to define the exponential objects in the category presheaves is to use the diYoneda lemma. So we do the kind of standard diYoneda trick of assuming that we have the exponential objects and then applying the diYoneda lemma and the universal property of exponentials to figure out what the definition has to be, and then we can turn that around and use that as the definition of exponentials in the category presheaves. And so interestingly, we can do the same thing here. but we need a ℂ lemma for difunctors. We need a diYoneda lemma. So here's the diYoneda embedding. So notice the form of this is that it's again has a contravariant and a covariant argument in the category, and then it goes into the category of difunctors. So similarly to how the ℂ embedding goes from the category to just has one variance from the category to the category presheafs, this is the difunctorial version of this. And there's not too much interesting to say about this particular definition. This is just kind of the definition that we have to give in order to make sense of in order for all this to work out. We just define it as, we kind of define it as this double Hom set, again analogously to how the ℂ embedding is defined by just one Hom set. We're doing both variances here, so it's two Hom sets. And all the morphism parts, of course, are given by the appropriate pre and post compositions. And so then here's our diYoneda lemma, and I have not seen this lemma at least stated in anywhere near this way anywhere in the literature. So if you've seen anything like this, I'd be interested to hear, because hard for me to believe that this hasn't been stated, because it's kind of basically you just take the usual ℂ lemma and the proof of it and carry out it in the way that just making the necessary changes. There's nothing too novel here besides just the machinery of difunctors and paranatural transformations. So what it says is that it's a ℂ lemma. It's that the applications of a difunctor is the same thing as transformations, in this case paranatural transformations, from these representable from ℂ of that argument into the difunctor in question delta. And so this kind of two things to note here about this statement. The first of all is that note that the J and the I here are flipped on the right. That's because we need to make this so this left hand side is contravariant in I and covariant in J, and so we need to match that here. And since this is appearing kind of on the left hand side of an arrow, or kind of in a negative position, we end up having to flip these. So that's one thing to be mindful of. But it's the other thing to know here is that this bijection, or this isomorphism here is a paranatural isomorphism. It's an isomorphism in the category of difunctors. And so in order to do this, this is just kind of a really quick sketch of what the argument looks like, but we're constructing paranatural transformations back and forth between delta and again, viewing this right hand side as a difunctor in I and J. So there we have our ℂ lemma, which I think is our diYoneda lemma, which I think is really cool. And then we can use that, like I said, to define exponential objects. And again, perfectly analogously to how we do it in the category presheafs. So we suppose that delta to the gamma, this exponential object exists, and then we apply ℂ and then apply the desired property that we can, this adjunction that we can pull gamma over onto the right hand side here as a product, and then this here we make no reference to what we don't make no reference to delta to the gamma, and so this is a perfectly fine definition for what delta to the gamma of ij is. And so we can make that our definition, and then carry through all the calculations, and construct the evaluation map and prove the appropriate universal property and all of that. So you can do that in this case, and so we get that this category has exponential objects as well. So like I said, it's a Cartesian closed category. And so I conjecture that this goes a little bit further, that we can recover even more of the nice properties of presheaf categories in this for this difunctor category. So I'm still investigating what sub-object classifiers look like, what limits and co-limits look like in this category. So I'll list this as a conjecture for now, but I believe that this analogy continues to carry through. And then another kind of result that I'm kind of still working through is the claim that so I mentioned the church numerals we can view, or the natural numbers, we can encode them as endotransformations of the Hom difunctor. And so my conjecture is that this exponential object Hom to the Hom it actually forms a natural number object in the category of difunctors. So I believe this is true. I haven't really sketched through all the details, so there might be some conditions that are required or some restrictions or whatever that's necessary, but I believe this to be the case. Okay, so I'm running low on time, so let me kind of get to my kind of punchline here, which is the question of is this actually a novel category theory? Are we actually doing anything new here? So in particular, what I'm really asking is paranaturality, as I've defined it, is it just an instance of naturality? And does that explain why we're able to do Yoneda lemma and this kind of category of difunctors? Is that just the usual Yoneda lemma, and is that just the usual category presheaves, just in kind of some bizarre disguise? So I gave a talk about the same topic about a month ago, and several members of the audience there were relatively convinced that it was, but we really struggled to be able to write down how. So this is kind of the question that I'm still open as far as I'm concerned, is that given these difunctors, can we view the set of paranatural transformations between them as just a set of natural transformations between some kind of modified functors delta gamma bar and delta bar? So again, I don't know if there's a way to do this in general. If there is, then there's no real need for a branch of category or a sub-branch of category theory known as paranatural category theory. It's just usual category theory just for this specific instance. And so in that case, presumably diYoneda would just be an instance of Yoneda, and this category of difunctors would just be equivalent to a presheaf category in some sense. But currently, I've been working under the hypothesis of a negative answer. And I don't know exactly what a proof of a negative answer would look like. Maybe there's, I'm not a topos theorist, so I don't know a lot of these really fancy properties of presheaf categories. But perhaps there's some property of presheaf categories that doesn't hold of difunctor categories, or some kind of invariant or something that we could use as a negative proof to show that paranatural transformations are actually a distinct concept from natural transformations and not just a mere instance of it. And in that case, then there is a need for a paranatural category theory. This is a distinct theory that needs to be developed more. So here's some kind of a bunch of things that I don't have time to talk about today, but I think are really interesting aspects of this theory. So again, there's equivalent ways of stating the definition of paranaturality, and in various guises depending on your tastes. There's this whole theory of the kind of category of elements, the analog of the category of elements, which I call the category of diagonal elements or structures, which have a nice theory, and in particular the category of structures of diYoneda would be these kind of direpresentables would be what I call splice categories, which kind of simultaneously generalize both categories slice categories and co-slice categories. And then I mentioned this earlier. There's this kind of, you can develop this whole kind of strong or kind of structural co-end calculus associated to this, which has a lot of really nice features. So yeah, what I call structural ends, and there's this, and you can prove that this really nicely captures the theory of initial algebras, and there's this nice Yoneda-like lemma due to Taranatural, and then you can dualize it to structural coends and get terminal coalgebras and co-induction and bisimulations and a dual of this Yoneda-like lemma as well. And then I'm also starting to work on this kind of a theory of dependent paranatural transformations. So in the same way we can define dependent natural transformations and kind of presheaves over presheaves, we can kind of start to do the same thing with paranatural transformations. And so I'm curious if there's a dependent diYoneda lemma. And so let me conclude by mentioning some of the applications of this theory. So it has some really interesting connections to the the categorical semantics of co-inductive types, like I just mentioned. And it kind of generalizes and dualizes this result by Audi, Fry, and Spite to do impredicative encodings of inductive and co-inductive types. There's this really interesting connection to parametricity that I mentioned. And so paranatural transformations encode like kind of a universal and existential types, like you might be familiar from functional programming. And so my general conjecture is that paranatural transformations correspond to the kind of the topic of parametricity. And so if you look at, for example, the free theorems of Phil Wadler, pretty much all of those are instances of or all the ones I've checked so far are instances of a paranaturality condition. So I think that's a really interesting topic that needs to be explored further. And then finally, you can do a difunctor model of type theory, which if paranatural transformations are just an instance of natural transformations, that would just be a presheaf model of type theory, but it might be a distinct theory. So yeah, here's a list of, I think I gotta cut myself off, but yeah, here's a list of various talks and presentations and stuff like that, including the archive link I mentioned. And there are some references. So apologies for running slightly over, but thank you all for listening.
So thank you, Jacob. If you've never been to a Zoom talk before, there's a way of electronically thanking our speaker. If you click on reactions at the bottom of the screen, you'll see a clapping symbol. You can clap on that and just imagine that that's making noise, Jacob. So we'll now open up the floor for questions, and Fosco has a question.
Yeah. In fact, the questions became two, but I'll just ask the old one. A good idea in the direction of studying the properties of your C diamond that I have tried to think about for a while is whether the category is locally presentable. Because that would be a very convincing argument, because you showed that it is Cartesian closed, and now in order to be not only an elementary topos, but a Grothendieck topos, it's enough that it's with a subobject classifier and it is presentable.
Yeah, so that's an interesting question. I haven't looked into like local presentability or anything like that, or yeah, well, I mean, yeah, I still need to establish that it is indeed a topos at all, but yeah, that would be like, yeah, trying to narrow it down. I mean, presumably if it's analogous to a presheaf category, it would be, you know, a very nice topos indeed. So I hope so, but we'll have to see.
Did you try to think about whether this sending C to C diamond is a KZ monad and the diYoneda embedding is its unit, for example?
I haven't looked at that. I'll definitely try to check that out for sure. Okay.
I think we should discuss extensively in private, because I have a lot of questions. I'm here because I have been reading your paper and I filled 5 pages of notes only with questions and interesting things that we can think about.
Well, I'm really glad to hear that. It inspired you that much. Yeah, definitely. I'll definitely get in touch with me, and we'll discuss this a lot more for sure.
Let's keep in touch. Thanks again for your time.
I think we can do one more question.
I have a question. Hi.
Go ahead, Luca.
Yeah. Difunctors should correspond via category of elements to two-sided discrete fibrations. I was wondering which kind of morphism between two-sided fibration corresponds to paranatural morphism. Transformation.
Yeah, I don't have a good answer to that. I mean, I've only looked a little bit at trying to find like some kind of like corresponding vibration condition. So I wish sorry if a lot of my answers here are, oh, that's interesting, I have no idea, but I think that's kind of a little bit of the nature of where things are at. So yeah, if I ever come with a good answer of what the corresponding vibration condition would be, I'll definitely put that update the archive preprint or something with that. So thanks for bringing that up.
Thank you.
Thank you, Luca. Phil, did you have a question?
Yeah, I did have. That was a nice talk, Jacob. I like that.
Thank you.
So I wrote one of the early papers that sort of started the subject, functorial polymorphism, with Shedroff and Baybridge. But I wanted to mention to you an interesting thing. If you wanted to look at sort of what might be the internal logic that you're getting at here, there's an important paper, and I don't have the reference, but I'll give you the name, A Logic for Parametric Polymorphism.
Okay.
And a body.
Mm-hmm.
In there, it uses two ingredients from our first paper, which Parker complained about. The first half was dinaturals, and the second half was Reynolds parametricity. Now, Reynolds parametricity doubles all the variables. So if you have a context, x1 to xk, you would take COp to the k cross DOP,
Mm-hmm.
And if you work that way, then the Reynolds parametricity, or stuff like the identity extension lemma and so on, you get kind of a relational interpretation. And then the question is, how does the dynat interpretation relate to the relational one? And they have a theorem, just a little remark in the paper, that Reynolds parametricity implies dinaturality. And so there's a whole kind of little theory about this that you might want to look at. And I think the answer is we don't know. The answer is that the logic might work for system F, but it's kind of a partial logic, and it's not clear what the logic would be, except I can say that the theorems for free is done even more generally categorically by Girard and Shedroff and I in a paper you'll find on my webpage. And we get all these theorems for free, but then it turns out that it's just because of a kind of triviality that you do exactly what you did. You look product and exponentials, and then you in the Gensen calculus, you write product and exponentials, and then you find a version of it that's presentable, that's cut free. And if it's cut free, then you don't have the cut rule. You don't have to worry about composition. So you throw everything away, and you get all of Wadler's theorems for free. But that tells you the logic is just simply type lambda calculus. So nobody knows what the logic in between would be. So that's not going to help you. System F is way too powerful, and the Cartesian closed structure is way too weak. So we don't. So I'm very interested in seeing what you come up with.
Yeah. Thank you for your comments, and thank you for your for functorial polymorphism. I definitely have spent a good amount of time looking over that paper, and it's a good read. So and this is definitely a big part of my motivation is trying to develop more some of this category theory towards answering some of these questions about, or building more of a category theoretic treatment of parametricity. So I'll definitely look at the references you cited. So thank you.